So it's my pleasure to start our seminar of this year with the speaker from the University of the Burgundy, yeah, Jules Martin. He shall speak about the modules of quantized Lie algebra and the braiding from homology of configuration spaces. Please, Jules.
Okay, well, thank you very much for receiving me. Thank you for people who woke up early this morning for listening to me. And thank you, Van, for the invitation. Okay, so because of these COVID things, etc., I'm forced to be far away from you, and I will have to stick with the slides you have in front of you. And I have problems with slides. My problem is that I always write too much on them because I'm always afraid you ask too much question and I have to answer it, blah, blah, blah. So that the counterpart of this is that I will probably have to skip some things, but I will let you know explicitly if I do so. So yeah, that's all I'm going to say. My title is Modules of Quantized Algebras and their Braiding from Homology of Configuration Spaces. So that I'm sorry, I know that your seminar is interested in cohomological structure. I didn't succeed in putting a co in my title, so I will only do homology things, but I really hope that all I will be I will be saying today have a dual version in some cohomological theory with more analysis, etc. So that if you have any hints, please help me. So the goal of today will be to compare two mathematical theories that I use to do low-dimensional topology. On one hand, you have quantum topology, and we will see why it is called like this. And on the other hand, you have a homology of configuration spaces. So the goal of today will be to relate somehow these two low-dimensional topology theory. And maybe a first good sign of these two directions is contained in the definition of braid groups. So let Bn denote the group of braids with n strengths, where r is an integer here. And let me give you two definitions of this object. The first one, I'm sure you have seen it once in your life. It's the Artin presentation of braid groups with n-1 generators, sigma 1 to sigma n-1, satisfying two types of relation. The first one tells you that two generators commute if they are not consecutive ones, while the second one tells you how behaves two consecutive generators, namely they satisfy an ABA equals BAB relation. Okay, and this one is maybe known as the braid relations. So this is the first definition. It's an abstract group, and let me give you another definition of the same group, but it involves some topology, so that I have to introduce a surface denoted Dn, which is just a disk with n punctures. So it has appeared here, down here, and also on the left, this is my MIMO then, where you will see that there will be notation appearing all along the top and staying until the end, so that you can refer to them anytime, instead of me going backward in my slides too many times. So this is the surface, the puncture disk. It's just, think of it as the unit disk, where you take n points inside of it. You can imagine them to be on the real line, and you remove them so that you get something which is non-compact. And this is this surface called Dn. I'm drawing square unit disk because I want to my pictures to be clear. But anyway, think of it as the unit disk. And then the group Bn is defined to be the mapping class group of this surface. So a standard definition for these mapping class groups is mod Bn. So you can define such a group for any surface here. And it's simply defined to be the diffeomorphism group of the surface, but you somehow consider this diffeomorphism up to isotopy, and the composition is the product. So here we have a boundary, surface with boundary, so that you ask that your diffeomorphism are strictly the identity on the boundary. So this definition could be extended to any surface almost. So, and it will be useful for some things I will say later on. And here, okay, and so these are two definitions defining the same group. And just to say, for your knowledge, you can actually relate these two definitions by sending the sigma I generator from the active presentation to the isotopic class of some special homeomorphism called half-den twists. Okay, just briefly, a half-den twist is a homeomorphism which is almost the identity everywhere, besides a disk surrounding these two punctures here. And it somehow gives pi rotation to this disk so that it swaps the puncture Wi in its neighbor. Okay. Anyway, it has a precise definition. I won't give it to you. I just want to mention it for people who has heard about these den twists. And it's just to say that you have a correspondence between these two definitions, and they are defining the same object. Now, of course, it's a theorem to show it, but anyway. What I wanted to say here is that you have two very different definitions of the same object, and by very different, I mean that the first one is purely algebraic, while the second one involves some topology, right? And so that we will see, I mean, the philosophy of today is that these two very different definitions of the same object will lead to two almost opposite directions to build representation theory of these groups. So that you may have noticed that when you want to study an abstract group, you are often interested in studying linear representations of this group. And we will see that these two definitions will lead to two different representation theory of this group. And for the purpose of this introduction, I want to talk about the first method, the algebraic method. So how would you construct a linear representation of this group? Namely, how would you assign to any braid a matrix so that the product in your group will be represented by the matrix product? Well, you can naively try to assign a matrix to every generators here, and then to translate the relation they must satisfy in terms of equation. And in the case of the braid groups, you will probably find a very famous equation, which is called the Young-Baxter equation, that comes from physics somehow. I won't write it down in front of you, but I just think that it translates in terms of operator the braid relation here, okay? The relation you want the braid to satisfy. And okay, so it was a long-standing problem to find solutions of this Young-Baxter equation for physicists and for mathematicians. They tried to find some by hand, but in the 80s, Drinfel'd found the nice algebraic setup where you find these solutions of the Young-Baxter equation, allowing you to build linear representations of braid groups. And this algebraic context is the context of braid groups, of quantum groups, sorry. So what is a quantum group? Just think that if you have your preferred Lie algebra, it lives, in fact, in a real algebra called the enveloping algebra of this Lie algebra. And you can quantize this construction somehow. I won't give the process to you, but you can quantize this construction and obtain a quantized enveloping algebra, which is still an algebra, but somehow more complicated on one hand, but richer on the other hand. So that the representation theory is a bit more complicated, but richer. And you can do so with any semi-simple algebra. Say semi-simple to be simple for today. So what Drinfel'd did is that for a fixed quantum groups, for a fixed quantum group plus a representation of this group, of this algebra, so you need the quantum group plus its representation theory as inputs. Then you can find solutions of the Young-Baxter equation and construct what we call quantum braid representation. This is the work of Drinfel'd in the 80s. And I want to talk about two other theories appearing in the 80s, apparently very disjoint for the one with the one I just described. The second one is the theory of knot invariants, and more precisely, the polynomial invariant due to Vogel-Jones, called the Jones Polynomial, which is, you know, knots are embeddings of circles inside R3 that you consider up to ambient isotopy. And you want to assign topological invariant of this, and Jones has provided a new recipe to do so. And from the beginning, his invariant has very new properties in comparison with what we were able to do before. But there was a mystery because his construction was roughly algebraic, so that in the end you don't know what topology is in there. Okay. And the third theory from the 80s, due to Edward Witten, it is called the Topological Quantum Field Theories. It comes from physics, but on the mathematical side, what you get from them is whenever you have such a theory, you get three manifold invariants for any three manifolds you want. And you also get mapping class group representations for all surfaces. So you can extend the definition of mapping class groups to any surface, and from these TQFTs you obtain what we call quantum representations of mapping class groups, which are linear representations of these groups out of these TQFTs. Okay, so these are three theories from the 80s. These three guys were honored by the Fields Medal in 1990. And shortly after that, these three theories were reunited into one package called quantum topology. First of all, because there is a topological operation to pass from braids to knots, which is called the braid closure here. I will maybe talk about it later on. And so you have this topological operation, and you can translate it in terms of equation. And okay, I'm quite loosely speaking right now, but anyway, you can translate it in terms of equation, and it's Reshetikhin Turaev in 1990 who succeeded in recovering knot invariants a la Jones from quantum braid representations of Drinfel'd. Okay, and they only used algebraic tools that are inside the category of quantum groups and their representations. Okay, and again, you also have a topological operation to pass from knots to three manifolds, which is called the dense surgery. Okay, and again, you can translate this in terms of equation, and again, Reshetikhin and Turaev found solutions of these equations inside quantum groups and representation theory, loosely speaking, and they recover three manifold invariants of Witten out of Jones knot invariants. Okay. And moreover, they succeeded in constructing the entire TQFT and recovering quantum mapping class representation. So that in the end, from your preferred quantum group plus some special representation of it, you can construct all these low-dimensional topological invariants, but it relies on inherent tools of the category of quantum groups modules, so that in the end, a lot of conjecture of the domain deal with what these topological invariants contain, topologically speaking. I summed this up in the following question: what is the topological content of UQSL2? This is not a conjecture not a precise conjecture, but it sums up the philosophy of the work in quantum topology. So I told you, if you take your preferred algebra, mine is the simplest, of course, it's SL2. So you have this quantized algebra that we denote UQSL2. And then you can construct all these invariants, and well, in the end, you have topological invariants, and you wonder what's the topological content of this algebra. So I hope we will have hints on to answer this question. And I want also to mention another big question surrounding mapping class groups of surfaces, which is a very, okay, so it's not only about quantum topology. Any people working with mapping class groups of surfaces, you have other theory to do so, are wondering whether these mapping class groups of surfaces are linear. Namely, can you see them faithfully as subgroups of transformation groups of linear transformation of vector spaces? Okay, so this is a very big question, and I think that this question is legitimate whenever you have good candidates, namely when you are first able to assign to any element of your group linear transformation, so that the product is represented, and so that this process is has good chance to be faithful. Okay, and I hope that we will see today some good candidates, but of course I'm not pretending I'm going to answer this question. Well, so if you don't have any question, I will skip this and go to my plan. So the goal for today will be to use homological theory, so for recovering these quantum topology invariants. So in my first part, I will present my homology theory, which is homology of configuration spaces, and I will study their structure. Then in the second part, I will present how, so I will derive from this homology of configuration spaces a way for recovering quantum braid representations. This will be the purpose of second part. Okay, and last part, if I have time, I will try to go to next step. Namely, you remember from quantum braid representation, you can get not invariants. And I will see how this homological model for quantum braid representations shed lights on the topological content of not invariants a la Jones. Okay, I put a 1 here and a 2 here because I will give references in the end that will be numbered 1 and 2. Okay, so if you don't have questions, I will pass to homology right now. And first, I will present how to construct homology modules. Okay, so as I want to do homology, I need a ground topological space to play with. Okay, and this topological space will be configuration space of points in the puncture disk. Okay, so I take my punctured disk back, so dn, which is still here on your left, and I define, and I also take an integer r, and I define xr to be the space of f tuples taken inside my puncture disk, and I ask all the coordinates to be different. Okay, this is configuration spaces, and I then unorder it by modding out by the permutation group of R elements, and this permutation group acts by permutation of coordinates here, so that after the quotient, the order of coordinates doesn't count anymore. You only have unordered configurations. Well, these are my the topological space I will be playing with until the end of this talk. But I don't want. Okay, I want to do twisted homology theory, and there is a nice setup to twist homology, to twist the coefficient of homology, using a representation of the pi1 of your topological space. So, okay, so this is just a remark. So first of all, to talk about pi1, I need a base point. And I denoted bulk CR. Maybe you have a question, Van? No?
It's CR or is PR?
Sorry?
The pi1 XR is a configuration space and psi R.
Yeah, psi R is the base point.
Okay.
Okay, so a base point inside the configuration space is in fact an R tuple
base point, yeah.
inside your puncture disk. And look, it has appeared here on the puncture disk. You have here an R tuple which I will use as a base point. So all the computations rely on the base point because it's easier to have a base point in fact. What I'm saying here is just that for people who knows about it, you can see these pi1s here of configuration spaces inside braid groups with R plus n strings. Okay. Anyway, I'll have to hide this because I don't have enough time to talk about it, but it's the best way to work with these pi1s. And then I want to define a representation of the pi1. Okay, so I will take the ring of Laurent polynomials into variables here, denoted R. And okay, this is a kind of a black box, but there exists a representation of your pi1, of the algebra of your pi1 inside this ring, inside this ring of Laurent polynomials. Okay.
I'm sorry, may I ask you?
Yeah.
So you have the n, so this is the disk with n punctures, so it's actually with n fixed endpoints, right?
Yeah, this n, okay.
But for some reason you add also r points, r more points, right? So
yeah.
And finally you have n plus r points.
Yeah. But,
why do you distinguish this between this n and r?
Okay, from now on, the w1 to wn won't move at any time, while the configuration points will be...
I see. So you fixed n and then r are moving. Okay, and then
you
take the quotient by sigma r. Okay.
Yeah, I will take one package of points of f points that will move inside my puncture disk, of course, avoiding to meet this w1 to wn, and also avoiding to meet one with each other. Okay, but there will be two indices that will play a different role in what I will.
And
say.
B is the braid group, right?
B is the braid group, yeah. And here it's the braid group with R plus n strings.
Yeah, with fixed. I see.
Yeah.
Okay.
but you don't take all the braids.
Yes, sure, because your endpoints are fixed.
Yeah, exactly. You take only the braids that fix precisely this endpoint.
Okay, I hope you explain later why it's needed. Thank you.
Yeah, there should be I is not equal to J in the definition of XR also.
What is J?
Yes, in the upper line, I is not for I is Zi is equal to Zi for sure, right?
Yeah, sure. Sorry.
Okay.
Yeah, thank you. Okay, so I'm hiding some things here, but of course, whenever you see the pi1 as braids, as we just mentioned, it's easier to define this representation by saying to what braids you send to what monomial in the ring of Laurent polynomials. Okay, but for people who are also aware of this, just think that this morphism here comes from the abelianization of the pi1 here. This is another way of defining it, but this is hiding more, I think. And anyway, what I want to recover from this, so from the theory of covering spaces, you know that for such a morphism of pi1, there is a corresponding covering of your space. Okay, I denoted hat XR, and usually it's defined, okay, with a lack of rigorousness here, as so you have tilde XR to be the universal cover of your space, over which there is an action of the pi1 by deck transformations, and then you mod out by orbits of the action of the kernel of, then you take orbits of the action. Okay, well, you mod out by kernel of OR. Okay, this is a way of knowing the covering space I'm working with. Okay, so
sorry, and what is XR tilde?
Tilde is the universal cover.
Ah, I see. Sorry. Okay.
These spaces have universal cover, and the universal cover, you have this deck transformation action. The pi1 acts on it by deck transformation, by transformation commuting with the covering map. Okay, and okay, you have a sub covering corresponding to the kernel of this morphism here, and you have a correspondence between these two. Okay, I will use many point of views for people. Okay, people knowing the covering theory or people preferring representations of pi1. But anyway, on this special cover hat XR here, you have the ring R acting by deck transformations. Okay, which is something we will have to remind for the next slides. Okay.
So you take the abelianization of the fundamental group,
yeah,
topic group. Then you take group algebra, and you have mapped into endomorphism of the ring as a module, or not into the ring itself, into maps on the ring.
Yeah, but endomorphism of R is R by this is saying that
of the fundamental group is not the first homology group.
Yeah, exactly. It's the first homology group, and so here there is a little lemma hidden saying that the homology group of the pi1 is dimension 2. Okay, you just have 2 copies of Z. One is generated by Q, one is generated by S, and when you take the ring of your group, you get the Laurent polynomial ring. Okay, but okay, this is to use big tricks. My preferred thing is to really define it explicitly using.
Is this theorem due to Arnold, Vladimir Arnold, if I remember correctly?
Sorry.
Who proved this about the braid group? Was it Arnold? Arnold.
What theorem? The fact that the abelianization of this is this?
Okay, not important. Yeah.
Okay. Okay. Well, if you don't have more questions, I will pass to homology, to twisted homology. So we define homology modules as follows. This is just notation, then I will describe them precisely. So I define H absolute R to be the number R level of homology of the space XR with twisted coefficient by the representation of OR I just not defined. Okay, so this is absolute homology modules. Then I also do relative homology. So I have to introduce a subspace of XR, denoted XR minus, made of all the R tuples that are in XR. such that one of the coordinate is fixed in W0, and you see W0 has appeared here on the left. So that you take all the R tuples having one coordinate fixed in W0. Just that. This is a subspace of XR. And you define H relative R to be the number R modulo of homology with XR relatively to XR minus twisted by rho R. Okay. I've encircled the letter R because here you see the index R refers either to the dimension of the homology and also to the number of configuration points you have taken in your ground topological space. Okay, this is somehow the middle homology of this space here. Okay. Okay, so now let me just briefly present what homology theories I'm using here. First of all, I told you I'm using twisted coefficients. So my coefficients are in the ring of Laurent polynomial R. And just to remind you briefly, it comes from the following complexes, or which one you prefer. So the complexes comes from are either you take the complex chain of your universal cover, upon which you have an action of the pi1 by deck transformation, and you make the tensor product with the ring of Laurent polynomial using the representation you just defined for the pi1. But you can also see it as the chain complex of hat XR, okay? And I told you upon this hat XR, you have an action of R by deck transformation, putting a structure of R module, okay? So that in the end, what you get is a chain complex. Your chain complex is a chain complex of R modules, and in the end, your homologies are R modules, okay? And also what I've hidden to you is that I'm using locally finite version of the homology, okay? We are dealing with non-compact spaces, and you have, I'm not using the standard singular homology, but I'm authorizing locally finite chains. Namely, I authorize I authorize infinite chains, so infinite linear combination of simplices, but I require their geometrical realization to be locally finite regarding the topology of XR. Okay, so this is usually used for this kind of non-compact spaces. What you get from this definition is that closed submanifolds, even non-compact, represent locally finite cycles. Okay, namely, if you have closed submanifolds but going to infinity, they have a class. They have a homological class. For instance, the real line has fundamental class. Okay, in this homology. Okay, so now I put all the notation here on the left. You have rho R the representation, the ring of Laurent polynomials, and from these two algebraic data, you can define the twisted homology of XR. Okay. Well, if you don't have question, I will now put a representation of braid groups on these homologies. Okay, this is a work due to Lawrence in the 90s. The group Bn, so the group Bn, the braid with n strengths, acts on the H absolute R. Okay. And with just a little more work, almost nothing to do, you can extend this action to the relative homology setup. Anyway, the important part is that what you get in the end is an action of Bn as R module transformation on these homology modules here, so that you don't only have one representation of your braid groups, but you have a graded family of representations because you can move the index R here and still represent the Bn group here. Okay, hope you're not lost. Anyway, so just a brief sketch of the construction to see where the second definition of the braid groups I gave you at the beginning appears. Well, so the second definition of braid groups I gave you is as a mapping class group. So you remember they are diffeomorphisms of your Parchin disk. So first of all, just think that braid groups are somehow diffeomorphism of your disk. So that homomorphisms of Dn, they extend naturally to the configuration space. You just apply your transformation to every coordinate, and you get a homomorphism of XR. Then the little work of Lawrence showed that you can lift your transformation to your cover and having an action on the twisted homology. Okay, this is the work of Lorentz, and by the fact that, okay, so here I considered homeomorphisms, but of course homology theory are isotopy invariant, so that in the end you get representation of the mapping class group and a well-defined action of braids on these homology modules. Okay, so this construction was due to Lorentz in 1990, but it got its notoriety 10 years after that, thanks to independent work of Bigelow and Kramer. They have shown that the representation of Bn on H absolute 2 is faithful. Okay, and this implies linearity of braid groups. So this implies that you can see braid groups are subgroups of matrices faithfully, so that this construction detects every braid. Okay, and so this is the first big example of mapping class groups that are linear. And so it legitimates a little bit the question I was asking in introduction. Okay, so this is the strongest result in the context of this question, whether mapping class groups of surfaces are linear. Okay. Well, in that question, just a little advertisement. I have a work in progress with Marco De Renzi, where we try to define, we succeeded in defining twisted homological representation of mod S of the mapping class groups of any surface on the homology of its configuration space. Okay, the twisting process is quite more complicated, but you can do it. And why are we doing so? First of all, because these homological constructions are good candidates for faithfulness, for obtaining faithfulness and then linearity of your thing, of your group. But also for people who know about it, and in the context of my introduction, we are going to recover non-semi-simple TQFT's representation. So you remember from your quantum groups plus representation, you can build a lot of in topological invariants. More precisely, you can build these famous TQFTs of Witten, and you have new TQFTs that were built recently that are called non-semi-simple TQFTs that are way richer than the one from the 90s. And we can recover them by homological construction like this. Okay, so this is just a little advertisement, then I will go back to braids. Okay, so let me talk briefly about the structure of these homologies. I will skip some things, but I want to first give you examples of homology classes, how to define homology classes in these complicated twisted homologies. Well, I will define homology classes from diagrams. So just look at this diagram here. It's a unit disk with two punctures related by a dashed arc indexed by R. Okay, so this is just a diagram. And on the other side, just think about the standard open simplex of dimension R, for which this is a standard parameterization. Okay, 0 less than T1 less than blah 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 less than TR less than 1. So this is a standard parameterization of a simplex of dimension R, open simplex. But you can also do the exercise in your mind to think about this parameterization here to be the space of configuration of F points inside the interval 0, 1. Okay, and if you do this exercise, thinking of this as the space of F tuples inside the interval 0, 1, you can send this interval 0, 1 inside the dashed arc here. And this defines you a well-defined embedding of a simplex inside your configuration space XR. So that this diagram here naturally defines an embedding of a simplex inside your space XR. Okay, this is what I said. And there's a little more work. I mean, it's just about the definition of the locally finite chains. I won't tell you more because I don't have time, but you can see that this simplex here is a cycle in the locally finite chain setup. Because boundary of these simplices are going to infinity, and you know it is a cycle. So it naturally defines a homology class here. But then this is only the homology with normal coefficients, and you want to twist the coefficients so that somehow you want to choose a lift of this simplex to your cover. And please believe me that the only data you need to choose a lift is a path from your base point to your manifold. Okay, so that this diagram here, the dashed arc plus what we call the handle, which is the path from your base point to your manifold. All of this setup defines you a class in H absolute R. So this diagram here, now that I explained to you the process, naturally defines homology classes. Okay, so if you believe me in the slides, you will believe me, I'm sure, that these diagrams here also defines homology classes. Okay, so you take dash arcs indexed by K0, K1, and so on until Kn minus 1, plus these red things going to the base point, or you take these arcs here, and it defines you whenever the sum of the Ki is equal to R, it defines you well-defined classes in H relative R, and they are indexed, they are parameterized by partitions of the integer R here. So this is the U family, and this is the A family, and you see the difference between the diagrams, okay? Now I'm able to state the structural result of this concerning these homologies. Namely, H relative R is a free R module. Secondly, the U elements that I've just presented to you is a basis. If you take all the partition of R here, so you have a free basis of your modules in terms of diagrams. And last but not least, why did I take only the middle of homology? It's because it's the only non-vanishing module in the homology series. Okay, all the homology is concentrated in the middle homology. Okay, in the middle dimension. Okay, I won't give you any hint of this proof because it's too long. But what I wanted to say is that you can easily, it's only topology. It's only retraction, excision, and this kind of process, so that you can generalize it whenever you twist coefficients with another thing. It doesn't rely on the algebraic setup you are using, and it's not relying neither on the surface. Okay, I mean you have you can extend it to other surfaces when we use it in some things. So we have the structure. We can also derive rules to do homological computation using these diagrams. For instance, if you have a diagram with dashed arcs going like this, you can express it as one dashed arc indexed by K plus 1, okay, whatever this diagram means here. And you can do retraction excision and show that the coefficient showing up here is this guy here somehow. And why I want to talk about this, it is because these guys are called quantum numbers. And for me, this rule here is the first sign of appearance of quantum topology, because whenever you work with quantum groups, all the combinatorial of quantum groups is made of these quantum integers. You see them everywhere. You have quantum factorials, quantum binomials, etc. So this homological rule involves quantum numbers, okay? Then you can also derive other diagram rules. Thanks to this computation, you can express the A family in terms of the U family I've introduced, and show that the A family also forms an integral basis of H relative R, because the change of basis is invertible. And also I have a paper of mine that provides concrete approach to the BN representation. Okay, namely, it gives bases and it gives matrices. All the computation, you can have matrices for these faithful representations of braid groups. Okay, this is again a little bit tight. But what I wanted to do today is to recover from these homology modules quantum topology. So let me do a first quantum interlude, so namely a crash course on quantum groups. And it goes like this. So you need, as input, you need an integral version of your quantum group. By integral, I mean that I want the coefficient to be the ring of Laurent polynomials here, so that I put this notation L over 2, but whatever it means, we don't care. So you take your quantum group. It has an explicit presentation with generators and relations. If you want to see it, you can go to my papers, for instance. But it's very, you see them in the literature widely. So you take this quantum group, this R algebra, but you also need one object in its category of representation, which is called the Verma module. Okay, so it's an infinite dimensional module. So in infinite dimensional vector spaces generated by V0, V1, V2, and so on. And you have an explicit action of UQSL2 on these vectors that you can define. What I want to say about these Verma modules, you can provide an explicit presentation, of course, but it's a universal object in the sense that for any quantum group, you have the Verma module, okay? And this Verma module somehow contains all the modules you need to do topology, all the weight modules for people doing representation theory here. Okay, maybe not all the weight modules, but the interesting ones. You also have them for standard Lie algebras, etc. So you take the Verma module, and then the work of Drinfel'd tells you that you have, if you want to have a representation, a linear representation of your braid group Bn, you will have to take the tensor product of n copies of your Verma modules. Okay, and then you have a well-defined action of your braid groups on this tensor product that commutes with the action of UQSL2, because this tensor product of Verma modules is also a module of UQSL2. Okay, so that your braid group acts as linear transformation. By linear, I mean that it commutes with the ring of Laurent polynomial structure, and also it commutes with the action of UQSL2. Yes, you have a question?
What is R1? Because it has some unit, I guess.
Oh, it's a mistake. Just remove the one, sorry. Because usually I use more ring, but for today I will use only one.
Okay, thanks.
Okay, this is the work of Drinfel'd, and this is my crash course on braid group representations on the quantum side. Just know that this tensor product of Verma module is infinite dimensional, but as a braid group representation, it splits in this W and R here, which are the level, and they are finite dimensional and indexed by R. So that in fact you have an infinite family of braid group representation indexed by R. Okay, and you can define this level using the UQSL2 action, but I'm hiding this. Okay, so I put this on the left here. You have the tensor product of n copies of Verma modules that is endowed with an action of Bn, and this action of Bn splits into finite dimensional levels. Okay. If you don't have any question about this crash course on quantum topology, I will go to the theorem. The theorem is that you can provide an explicit morphism here, sending your homology modules. You send the A family of diagrams for any partition here, K0, Kn minus 1, you send it to Vk0, blah, 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 Vkn minus 1. These Vi's here are the one usually used to define the Verma modules, so that you have a NAR modules isomorphism, because this is the basis of your R module here, and this is the basis of your R module here. And it is Bn equivariant, respecting the grading, namely each of the level here is isomorphic as a Bn representation with this guy. And it also intertwines a new homological UQSL2 action. By new, I mean that you have to define an action of UQSL2 with homological operator on the left side here. And what you get is a full homological model for this tensor product of Verma modules. Okay. Okay, so the proof is first defining a homological action of UQSL2, then compute all the action on the A basis I've given you and compare them to the formula you have on the quantum side, and you can find all of this in the paper 1. Okay, if you don't have questions.
Yeah, sorry again. Can you say what A basis is?
A basis. So here on the left you have the U basis. You remember? And the A basis was just a change of diagram.
Yeah.
Let me go back. Okay, so these guys were the A's. You're just changing the diagrams, but you can define homology classes naturally, as I did also with these guys. Okay. Thanks. Just to have the one-to-one correspondence between the traditional basis of Verma modules and homology, you have to take the A's. Okay. And actually, this is very important because you have to find these guys to recognize Verma modules. Okay, I'm not going to say a lot more about how to define the UQSL2 action on the homological side, but if you want to see precise definition of homological action of UQSL2, you can go to the paper 1. Let me just give you an example, just saying that UQSL2 has a finite presentation with generators and relations. The generators looks like the usual ones for SL2. We call them E, F, and K. And for instance, the action of E is somehow the boundary map from the relative exact sequence in homology. You know, you have a long exact sequence whenever you do relative homology, and you have this boundary map that sends your relative homology modules to the relative part and decreasing the dimension by 1. And then you have a little isomorphism to identify this guy with this guy. What I want to say is that just think that every generators of your quantized algebra has a homological definition, okay? Namely, for instance, E is the easiest to describe, so that I chose this one for today. It's the boundary map from this relative exact sequence in homology, okay? F, the generators F are a bit more complicated to describe, but it's geometrical, okay? Just a little word on how to generalize this to other Lie algebra, because for today I used the Verma module for UQSL2. This is a joint work in progress with Professor Stefan Biglow. So just for people knowing Lie algebras, you know that if you take G to be a semi-simple Lie algebra, I take them semi-simple for today, it is determined by a set of simple roots, pi, alpha 1 to alpha L here, plus a Cartan matrix that I denote C. And this Cartan matrix contains somehow how you pair these simple roots here. Okay, so just think that my semi-simple algebra is given by this set of simple roots and a Cartan matrix C, and it defines a semi-simple algebra. Of course, it also defines the quantized version. So the quantized algebra denoted UQG traditionally, which is, well, the quantum group associated with this semi-simple algebra. Now let C be a coloring. So what I call a coloring is a map from the set of simple roots to integers. Okay. And you define R to be the sum of the C alpha I. Okay, so you assign an integer to every alpha I, to every root, and R is the sum of all these integers. So that you can think of this map as a coloring by roots, namely it's a partition of R by function on the root. Namely, so you can think of this as a way to color points. So if you have R points, you will have C of alpha 1 of them colored by alpha 1, C of alpha 2 of them colored by alpha 2, and so on, so that the sum is R. And this is how we are going to generalize the definition of configuration space. We define conf C, the space of configuration associated with the coloring C, to be the set of R tuples inside your puncture disk, where again you ask that all coordinates are different. And you mod out, this time you don't only mod out by all the permutations, but you mod out by these permutations here. So the permutation of C of alpha 1 element times blah, 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 times the permutation of C of alpha element. So that in the end, you have several packages of undistinguishable points, okay? You have a package of C of alpha 1 points colored by alpha 1, C of alpha 2 points colored by alpha 2, and so on. Just think that you embed points inside your puncture disk, but they are colored by roots, okay? So if they have the same color, they are undistinguishable. If they have different color, you can distinguish them inside your punctures. So this is how you generalize the notion of configuration spaces. So you see in this definition, only the set of roots is involved. But to define a quantum group, you also need the Cartan matrix. So then you have to define a new representation of your pi1 of conf C inside the ring of your own polynomials, as we did for SL2. And I'm hiding again this, but just think that it involves the data of the Cartan matrix. Okay, so that you have a generalization of the notion of configuration spaces, a generalization of representations of pi1 I used, and then in that spirit, you define H relative C to be the number R level of homology of conf C relatively to conf C minus that has the same definition as before, twisted by rho C, and rho C, I forgot it, but it's that representation. Okay, So you have a new configuration space, a new representation of the pyramid, but in the end, you have same kind of homology modules. And what we are doing is taking the sum of all colorings of these homology modules and endowing them with an action of UQG, homological action inspired by what I did for SO2. And in the end, we recover that this homology modules here is the tensor product of Verma module of UQG. And of course, this isomorphism intertwines the three action, the Laurent polynomial action, the UQG action, and the BN action. Okay, so this is just to say we have finally very equivalence between the theory of Verma modules of a quantum group and the theory of generalized configuration spaces. You can recover all you can build from them using these generalized things. Okay, so if you don't have question now, I will spend the last 8 minutes trying to tell you how these homological interpretation of Drinfel'd work can pass to the next step, namely to knot invariants. Okay, so I need to do a quantum interlude 2 and to give you a crash course on how to construct the Jones invariants of knots. Okay. So first of all, I want to describe how to pass from a braid to a knot. Okay. So look at here. This is a braid diagram, braid with 2 strands. Okay. So this is representing braid in B2. Okay. More precisely, this is sigma 1 cube. Okay. You see, you have 3 times 3 crossings here. So in B2, you only have 1 generator, and you have applied it thrice here. So this is a braid diagram, because I didn't tell you, but you can represent braids by braid diagrams, which is somehow the projection of a 3-dimensional object that you considered up to isotopy. Okay, and you have a standard way to close this braid, which will be appearing in a moment. Just now, this is a canonical way to close your braid. And whenever you do this closing process, what you get is an embedding of circle inside R3 that you consider up to isotopy, and this is defining a knot. Okay, this is how you define a knot. You can define a knot out of a braid closure, and this is what I'm going to consider today. So from now on, K will always be the closure of a braid beta with n strand. Okay, whenever you see in the formula K and beta, they will be related by the fact that K is the closure of beta. For instance, what you get from the closure of sigma 1 cube is the trefoil knot, maybe the most known non-trivial knot. Okay, the first one. Okay. So let me define a notation. I will denote JK of n, the nth colored Jones polynomial without an S here. Sorry. So in fact, shortly after Jones' work, we found out that Jones has not created one polynomial, but a whole series of knot invariants indexed by integers that are called the colored Jones polynomial. And for any integer here, you have knot invariants, which is polynomial in the variable q. And if you take n equals, I don't remember if it's 1 or 2, you get the usual Jones polynomial, the formal one, the initial one. Okay, so this is just a notation. I won't give a precise definition, but I will introduce it in a second in another way. But just because at the beginning I told you that a lot of conjectures in the domain are dealing with the topological content of these algebraic invariant. This is one famous example surrounding the knot invariant theory, is that this family of colored Jones polynomial, whenever you evaluate them at q, which is the variable of the polynomial, being equal to the nth root of unity. So this is a family of knot invariants, which are complex numbers indexed by n here. If you take this family, the conjecture says that it contains the hyperbolic volume of the complement of the knot inside R3. Okay. Well, this is loosely speaking. Of course, you have to define how it contains it, and I'm giving you hints here. It contains it in its asymptotic behavior in the variable n. Okay, but well, this is maybe the well-known volume conjecture, saying that, for instance, quantum knot invariants contain the hyperbolic volume of the complement of the knot. Okay, This was just for culture. And now a little lemma for today. So it tells you how to construct these color Jones invariant out of braid representations on quantum groups. In fact, you to define a not invariant out of braid representation, you somehow take the trace of the representation. So Q beta here is the representation of my braid beta. So it's a matrix using the tensor product of Verma modules. You precompose it by an operator here. I don't want to discuss it, but then you take this trace here, and what you get is a polynomial invariant. Of course, I told you that the tensor product of Verma module is infinite dimensional, so that to get a well-defined trace, you have to sum only over the first levels. And if you first over the n times big N first levels, you get the nth Jones polynomial. Okay. And also, you remember in the ring of Laurent polynomials, you have two variables, so that this trace has two variables, but you do s equal q to the power n, and you get a single variable polynomial, which is the Jones polynomial. Okay. So this is the philosophy somehow to obtain not invariants out of quantum group representation. What you have to do is to take the trace and do some arrangements. Okay. So this is not the first definition, but this is the one I will use for today. I compute the Jones polynomial out of Verma modules, although usually people are doing so using other modules, but this is to say that Verma modules contains anything you need to do topology. And now I will give only one interpretation of the Jones polynomial. I told you, you see, we expect it to contain some topology, but we don't know what. Maybe a first interpretation is the following, is using Lefschetz numbers. So let me give you the formula and then explain it. If you take the L+1 Jones polynomial of the node K, it is equal to some invertible coefficient. I don't want to discuss it. It's easy to compute. Then 1, which is also easy to compute. Then this sum, which is interesting, which is the sum of this LH of beta R, where beta R is the homomorphism associated with beta, namely you take the braid acting on the puncture disk and you extend this action to the configuration space. What you get is a homomorphism of XR here. And LH is what we call its abelianized Lefschetz number. Okay, and you have a weighted sum of these guys, of these abelianized Lefschetz numbers. Okay, so let me give an idea, a brief idea of the proof, and then tell you, okay, and it will tell you what these abelianized Lefschetz numbers are. Okay, so if you know the traditional Lefschetz formula in homology, you know that you have two ways to see Lefschetz numbers, traditional Lefschetz number, either as a trace on homology or either as a counting of fixed points, of indices of fixed points. So let me give the first definition. LH of beta R here is defined to be the alternated sum of traces of the action of beta lifted to homology. Okay, so this is, you can take it as a definition of abelianized Lefschetz number. Why are these guys called abelianized? Is because you lift the action of beta to the twisted homology by the maximal abelian cover. Okay, you lift the action to the maximal abelian cover. And so what you get is a polynomial in the ring of Laurent polynomial here, because coefficients of this action are inside this ring. Okay. So this is the definition of abelianized Lefschetz numbers. But because of what I told you in the structure of these modules, you only have one non-vanishing modulus here, which is the R-dimensional one. So that in fact, this alternated sum here is only the trace on the R modulus here. And because of the fact that the action of beta on homology modulus is the same as the action of beta on quantum modulus, what you get is that this trace here is equal to this trace here on the quantum side. And if you rearrange everything, as the Jones polynomial is a trace on the quantum side, what you get in the end is a formula here. Okay, of course, I'm hiding a lot of rearrangements of parametrization and blah, blah, blah. But in the end, you see that computing the trace, giving you the Jones polynomial, is equal to computing a homological trace, and you can interpret this homological trace as an abelianized Lefschetz number. And then what you get is the other definition of abelianized Lefschetz numbers, telling you that abelianized Lefschetz numbers are computing what we call homological Nielsen classes of fixed points of your homomorphism. So that this is the first interpretation you can have, telling you that the Jones polynomial of the knot is computing some Nielsen classes of fixed points of the homomorphism defined by your braid. Okay. I wanted to give you another interpretation, but I will skip it using Poincaré duality on homology, but I expected to have a cohomological version at some point if you are interested in, where you can express the Jones polynomial as an intersection pairing between fixed homology class. Okay, you know that you have an intersection pairing comes from Poincaré duality. And so you can make this Poincaré duality between two fixed class where one is moved by the action of beta. Okay, and okay, you can do the computation with diagrams and in the end reobtain the Jones polynomial, but I'm skipping this part and I will thank you for your attention.
Thank you very much, Jules. Yes. So let us thank the speaker and Petra.
Yes.
Do you have some comment?
Well, maybe I could ask something. So
Yes.
So I don't see what's the reason to use just Verma modules. They are quite special representations. So that's because the corresponding representation of the braid group is computable, or what's the reason for that?
Oh, the reason is that these homology guys are the Verma modules, first of all, but also on the quantum side, what we use to do topology, to define knot invariants, etc., and to build TFTs, etc., are, for instance, the Jones modules of UQSL2, which are finite dimensional modules, but you can see them inside Verma modules. This is somehow what I did here when I told you that to recover the Jones polynomial, you have to take something on the Verma modules and then to specialize the second variable to be this guy. In fact, what's hidden in this lemma here is that I can compute the trace of these precise that are called fundamental modules of UQSL2.
Okay,
you can compute them inside the Verma modules.
Yeah, so what's the key? So is the key point? Is it which makes it useful, those Verma modules, that they are highest weight modules? Or I don't see what's the point to use the Verma module, just the Verma module, because there is sort of reasonable category which contains Verma modules. It's called category O. So I don't see, which contains also finite dimensional representations. And by the way, Verma modules, when you take the maximal quotients, also contain or lead to finite dimensional representation. So I don't see why to use just Verma modules. So what's the key technical points which is useful from the point of view, from the perspective of the action of the braid group? So that was my question. So if there is some reasonable answer for that.
I hope that from the homology modules I've described, you can recover any modules from the category O. Okay, this is because you recover Verma modules, but I'm not saying that what I said is true. So this is on one hand. On the other hand, okay, so Lawrence, I mentioned Lawrence that has constructed this braid representation on the homological side at first. Her goal was to recover the Jones polynomial at first. So that, but it was not explicit. So people were wondering if what she was saying was true. And so that there were signs that these homology modules contain the fundamental representation, so the usual finite dimensional representation you use to compute. In fact, you recover something bigger, which is the Verma modules.
Sure. And
the interesting part on these Verma modules is also that you can specialize. You can specialize both variables. If you do S equals Q to the power n here, what you get is the fundamental thing allowing you to compute Jones. But if you evaluate Q instead of S, if you let S to be formal, and you put Q equal a root of unity, what you get is what we call the semi-simple quantum theory. Okay, a non-semi-simple quantum theory. So it corresponds to UQSL2 at roots of unity, and this category is complicated. The category of modules of this thing is complicated, but recently people have succeeded in doing topology with this this category. For instance, you have the corresponding knot invariants that are called colored Alexander invariants, and you can compute them by taking the Verma modules and applying Q to be the root of unity. And somehow, and it gives the non-semi-simple TQFTs that are very new developed tools. Well, so these Verma modules are two variable thing. And if you specialize one variable, you get to the Jones formalism. And if you specialize the other variable, you get to the non-semi-simple formalism. And you can do topology in both directions. And well, actually, I have a work in progress where we define a knot invariant as a trace of the action of beta on the entire Verma module. Of course, you have something which is infinite, a summation which is infinite, but you can give it a sense in terms of convergence in some completion of the ring R here, and prove that this converging series is a knot invariant. And in fact, this knot invariant is a unifying knot invariant. This is a work, I have a slide, I think. This is, yeah, exactly. This is a work in progress with my little brother, academic brother, Sonny Willits. He has created this invariant on Verma modules, which is a series, converging series, which is a knot invariant. And it is called the unifying invariant because it contains all the knot invariants you can define with QSL2. The Jones setup or the non-semi-simple setup where you evaluate Q at the root of unity. And we expect it to have extension to higher things, maybe quantum representation of mapping class groups, the TQFTs, etc. So that this Verma module somehow contains, this is why I said these Verma modules contain all you need to do topology. I'm not coming precisely from representation theory. And actually, I don't like the category O, I think, because to do precise topology, we need duality, right? We need to be able to evaluate a module against its dual. And I think that dual of Verma modules are complicated. Also,
there is duality, so it's as complicated as Verma module, so it goes in the opposite way in the sense of weight ordering and so on and so on. That's
yeah, but for instance, I think they are not in the category O, and so that I don't like the fact that you don't have duality in the category O, although you have it on the homological side. If you want to do if you want to do computation of a module with his dual, you can use compare duality. Sometimes it doesn't work, but usually it works. And if you work a little bit, it will work, and you will be able to compare a module with its dual.
Okay, is there no more question? So let's.
I have maybe just a remark that to recover the Jones polynomial only in this in Q, let's say there is this duality between some quotients of Weyl group or symmetric group, actually symmetric group, permutation group, and SO group. So you have tensor representation of SO B for binary form B, and then you can do the tensor representation of the kth product of B, and then you can compute the commutator. I mean, everything what's the commutant of this action, and you recover something like quotients of symmetric. You recover some quotient of symmetric group, which is usually it's usually depicted similar as two braids, and then one can recover the Jones. It's quite classical, and it should be also inspired by Markov. Yeah, so, and it's described in a book of Nolan Wallach and Roe Gutman. But there is actually no Verma module in this first book. It is called, it has two serious invariants. Sorry, I have it here. Symmetry, representations, and invariants. So chapter 10.4.
Yeah, sure.
And it's interesting that the solutions of young Baxter itself, with all this additional S probably, can be recovered by only the duality of SO and the quotient of permutation group over a subgroup, some double quotient, which has a name I unfortunately don't remember yet. No. So it has a classical analog with all this Verma modules actually directly. That's a remark. That's a remark.
Yeah, thank you. I'll look at this construction of.
Yeah, so it should be inspired by Markov. That is what I remember.
Okay.
The double quotient is somehow classical, but it's, I guess it's not Brett. So.
Okay. Thank you.
Is there some more questions? If not, then let us thank the speaker again, okay? So. And also thank you see what the reaction in the Zoom if you have some new version of Zoom.